On the units of rate of the reaction. So rate of the disappearance of R minus delta R by delta T and rate of appearance is delta P by delta T. So from this equation it is appeared that the unit of ray or concentration, that's per time, inverse of time. So for example, if the concentration is in mole per liter and time is in seconds, then the unit is mole per liter per second. However, in gaseous reactions, when the concentration of gas is expressed in terms of their partial pressures, then the units of the rate equation will be atmosphere per second. So here is the concentration. So I am trying to show the average rates of hydrolysis of butyl chloride. You are able to see the concentration of the reactants is reducing. The value is reducing. Obviously the product, the overall rate of the application or the process is getting reduced once the time is getting increased. So the reactants concentration reduced, so the rate of the coming out product is reducing. It can be seen that the average rate falls from 1.90 into 10, this one is 10 power minus 4 mole per liter per second to 0.4 10 power minus 4 mole per liter per second. So average rate cannot be used to predict the rate of the reaction at a particular instant, as it would be constant for the time interval for which it is calculated. So to express the rate at a particular moment of time, we determine the instantaneous rate. It is obtained when we consider the average rate at the smallest time interval, say dt, when delta t approaches 0. So mathematically, for an infinitesimally small dt, you'll be getting the average rate as minus delta R by delta T is equal to delta P by delta T. As at delta T is equal to 0 R instantaneous is equal to minus d of R by dt is equal to d of P by dt. This is the instantaneous rate. So it can be determined graphically by drawing a tangent at time t on either of the curves for concentration R and P versus time t and calculating its slope. So in problem 1 you got R instantaneous rate is 600 seconds. For example, can be calculated by plotting the concentration of butyl chloride as a function of time. A tangent is drawn that touches the curve at t is equal to 600 seconds. So the slope of the tangent gives the instantaneous rate. So R instantaneous at 600 seconds is given by 0.0165 minus 0.037 divided by 800 minus 400. You got 800 here and starting from 400 here. So cancelling this one, you got 5.12 into 10 power minus 5 mole per liter per second. At t is equal to 250 milliseconds, so 250 seconds. Our instantaneous value is 1.22 into 10 power minus 4, and at 350 over here you got 1.0 into 10 power minus 4 at 450 here. You got 6.4 into 10 power minus 5. So let's consider the equation. The mercury with chlorine gives mercury chloride. So over here the rate of the reaction is calculated as minus delta Hg divided by delta T, this one. So you got delta chlorine divided by delta T is equal to delta of HgCl2 divided by delta T. The rate of disappearance of any one of the reactants is same as the rate of appearance of the product. Either one of the reactants gives the product. But in the following equation of 2 moles of hydrogen iodide decomposes to give 1 mole of hydrogen and iodine, this is different. Let's move on. For expressing the rate of such a reaction where stoichiometric coefficient of reactants and products are not equal to 1. So the rate of disappearance of any of the reactant or the rate of appearance of the product is divided by their respective stoichiometric coefficients. So this is the main conditions, you should note it down. So as I indicated, the rate of consumption of hydrogen iodide is twice the rate of the formation of hydrogen and iodine. To make them equal, the term delta Hi is divided by 2. You can see it here. So this is the rate of the reaction. Minus indicates it's decomposed to form this one. So minus of half is equal to, this is the actual equation. So let's move on to the different equation. My bromine reacts with the bromate in the presence of hydrogen to form bromine and water. So these are ions. Bromine ion, bromate ion with a hydrogen ion forms bromine and water. So this is really different. You got the rate as 1 by 5 of bromine ion with 1 part of bromate with 1 by 6 part of hydrogen ion joins to form 1 by 3 of bromine and 1 by 3 of water. This is how the reactions are. Let's discuss more on the activation energy. So let me tell you a 3D of how the graphical view of activation energy is. I got the reactants, the energy which is required to make the reactants to react together to become or to get the products. That's referred to as activation energy. Here is the activation energy. By definition, the energy used to convert your reactants to products simple. So for a gaseous reaction at constant temperature, the concentration is directly proportional to the partial pressure of the species, and hence a rate can also be expressed as rate of change in partial pressure of the reactant or the product.